Hello, guys. A very good evening to you. And so, while I was doing a probability problem on a countably infinite set, natural number set, then I faced with an interesting idea, and also um, that is a very essential connection to something called Borel cantilever in probability theory. We will be doing a problem. We're sharing a problem, uploading a video on this, on the upcoming days, and how it's related to each other. But uh, in the very core of that, there is a problem which is very fundamental and a very beautiful result of a convergent series, and we will explore that. And this is really this requires an application of Cauchy sequence, and how everything you know just falls into the place and giving out to be really interesting intuitive results. That is the goal of this short video lecture. So let's get started. The question is the following. So if you have a sequence, let's say AI greater than 0, and you have this, that summation of I from 1 to infinity is convergent. Okay. So we have that, we have, just a minute, let me check. Yes. So we have that. So the question is that this is convergent. Okay. So let's say it's equal to L. The question is this, that uh, you know does what is the limit of n tends to infinity, or whether the limit exists when you take I from n to infinity. It's like it's like we are taking the tail of that. Okay, we are understanding the tail of the sequence. We're trying to understand how the tail is behaving, where the tail is going to. And we can show that mathematically this goes to 0. It's like, it's very beautiful. Okay, it's not always so intuitive, because if you know probability theory, the tail of the tail of a probability distribution may not always go to 0. So as limit goes to 0, so that's like a kind of an interesting idea. So here it goes to 0. So, and um, that's really important. And actually the tail of a probability distribution will go to 0. My idea is that the tail of a function may not always go to 0. Okay. So that's pretty interesting, and we will see this in the discrete framework, why the tail of a sequence, if it's, the summation exists, then it must go to 0. Okay. And this is pretty exciting. So let's get started, guys, and let's try to understand this very carefully, and we'll see all the action of Cauchy sequence very fundamentally rooted in this. So we want to show that this limit is 0, and the tail of this, I hope you understand the tail, because it's going from n, okay, to infinity, and it's like we're taking the upper hand. The first part of the sequence is I from the entire sequence series. The second is starting from 2. The third is starting from 3. So it's like we're taking the tail, not the not the, I mean, that's the definition of a tail. So now observe that if you understand it very carefully, as n goes to infinity, in some sense, the limit is going towards a n. Okay, in some sense, and since it's going towards the an, and you can observe this is a convergent sequence series, so the an must be going to 0. So in that sense, you can kind of get an idea that why this is 0. Okay, because as you take n tends, as the n becomes larger and larger, it's the series, the partial sum is becoming like an and an-ish. So that's the idea. It's becoming an-ish. Okay, so by an-ish I mean it's becoming like an, behaving like an. So let's try to prove it, and this is very important. The proof is very essential. You will understand how to prove these things. It's very pretty important. So we will see this application in Borel lemma and other probability problems I will be doing and uploading later on in this YouTube channel. So stay tuned and let's get started, guys. Okay. So first, define the partial sum. It's summation of I from n to infinity ai. So observe that, observe this following thing, that we know that, let's take this. So let's take the capital AN, which is nothing but the partial sum from I to 1 to n. Okay. Now we need to show what. So let's try to understand, recapture the Cauchy sequence ka definition. And you know, every convergent sequence is a Cauchy sequence and vice versa. So if you fix epsilon for all epsilon greater than 0 that exists in epsilon, such that for all n greater than or equal to n epsilon, you know, the distance between am and an, m comma n greater than or equal to n epsilon, the, you know, the distance, the relative distance between the two m and n, an and mn, is less than epsilon after a certain point. This is the definition of Cauchy sequence. Now Sn is convergent, it's given. The Sn is Sn we need to find out. I'm sorry. The An is convergent, it's given. Okay. So we need to prove Sn ka convergence, right? So therefore we need to show that. So the idea is that, understand this very carefully. We know the convergence of this An. Okay. So therefore somehow we have to boil it down, the convergence of Sn to the convergence of An. The understand the mathematical idea. We need to try to extrapolate, the try to, you know, connect the convergence of Sn to the convergence of An. That's the idea. Okay, understand it very carefully. So let's try to do it. Let's try to do it, and let's try to understand how convergence of Sn is related to convergence of San. Okay, so Sn. So we need to show that Sm minus Sn. Okay. So before doing that, let's try to understand this, that let's take An. It's nothing but summation of 1 to n ai. So observe that you can break it up into two parts. Summation of I to capital N ai plus capital N minus 1 and plus I from n to small n ai. Similarly, we can break it up into am into summation of I from 1 to mai is equal to I from, the first part will be the same. Of course, m and n greater than or equal to n epsilon. So we are trying to get that m over here into mai. Great. So observe that if you subtract this two, an minus am, or yeah, if you take this modulus, you will see this two term will get cancelled. What we will be left with are, observe, it's nothing but summation of ai from m n to m. Pretty great. Pretty great. Now, if you try to see, this is nothing but, you know, let's assume that m is greater than n. Let's assume that, or n is greater than m. Let's assume that. So we get the following, that it's summation. It's starting from n, so it's summation in some sense, ai, I from m or n to, let's assume n is greater than or equal to m. Okay, just like to make algebraically easier, n is greater than m. So it's like it's starting from m to n, and it's nothing but, observe, it's the same thing as summation of ai, I from n to infinity, minus summation of ai, I from m to infinity. modulus of that. So this is nothing but summation of Sn minus Sm. Understand it very carefully what's happening. So the idea is very fundamental. We are showing that modulus of An minus Am is nothing but Sn minus Sm. This is the idea. The consecutive difference between this M and An difference, understand it very carefully. We did it this, and when we do Am minus An, it's nothing but it's just taking from the summation from M to N. And similarly, when we do Sn minus Sm, since the upper part is the same, the summation is also the same. Like the distance, the modulus of that is also same. Okay, the distance between Sm and Sn is also the same. So therefore, the difference between An and Am and the Sn and Sm are actually the same modulus distance. So this leads to the idea that therefore, since An is convergent for all epsilon greater than 0, so let me write it down in a different. Since An is convergent for all epsilon greater than 0 that exist in epsilon, such that for all m comma n greater than or equal to an epsilon, modulus of Amn is less than epsilon, and since Amn is equal to Sm minus Sn is also less than epsilon, and therefore by the same definition we get that Sm is convergent, Sn is convergent. This is convergent. This is pretty interesting, right? Just one step. Now what is the limit? Why is the limit going to? This is pretty easy, because since the limit is convergent, you can now show that Sn is nothing but what? An plus Sn minus 1, because, or Sn plus 1, right? Sn is equal to, we check the An out and we get it starts from An plus 1, so An it's Sn plus 1. So since the Sn limit exists, we get that am I doing it correctly? Yes, I'm doing something wrong. Yeah. So how to show the limit exists? What is the limit? So you can show it by this method that, let's try to understand Sn. Now why Sn is going towards 0? So we have understood till this point of time that Sn is actually, okay. So let's understand this, at An, or summation of n from 1 to infinity, An is equal to yes, this is equal to An. So that's what we get. N plus like this one, summation of An, n from 1 to, let's say, some capital N plus n minus 1 plus summation of n to infinity n. It's getting, this is nothing but L is equal to, this is nothing but An minus 1 plus Sn. Now if you take the limit on both sides, you get therefore that L is equal to this limit, An ka limit is L again, plus Sn ka limit, and therefore Sn ka limit must be equal to 0. So therefore we get that Sn must go to 0, and this is a pretty interesting idea. So in fact, our intuition actually matches with this. So the question I will leave you with to ponder upon, to think, it's a food for thought question, is that if you know that Sn is going towards 0, the sequence is going towards 0, does it mean that AI is the series summation AI is convergent or not? If not, if yes, give a proof. You can just write your solution down and upload in a Google Drive and share it in the comments, or you can just give a counter example why it does not hold. The proof is left to you. So I hope you enjoyed this. I hope you learned a bit something new, how the tales of a in some sense you can also extend this idea to that to a probabilities. Okay, probability on a countably infinite set. So if that is the summation of the AI can be written as pi and it's going to 1, the L is equal to 1. So in that, the tail probability is actually going to 0. Also you can apply, just think about in the continuous version, if integration, okay, think about the continuous version. If integration, fx, let's say x from 1 to infinity is, let's say L, does it imply that limit, let's say t tends to infinity, integration t to infinity fx, this goes to 0, does it imply, like assume that fx is greater than 0? Okay, you think about the continuous version of it. So I leave you the 2 food for thought questions, because if something holds, it's like you're gonna, as you extend this to the fact that if a random variable has a continuous PDF, then the tail probability is actually, this is nothing but tail probability if fx is equal to the PDF is actually going to 0. Does it always happen? If yes, if no, why? If yes, why? So think about this question. So all the best, guys. Hope you enjoyed this and try to understand. And this is a very important. There's a topic called large deviations, where you will try to understand about the tail probability behavior, and in network analysis, network science, and random graphs, we try to understand the tail probabilities because it gives an upper bound to the probabilities. Okay, that's why this is a very important question to ask. Next, we ask at what rate the probability is going to 0, and this is going, the tail things are going through. So there are various kind of questions we ask. There's the various core ideas that we can explore, and try to think about this, guys. Take your time, and yeah, all the best. And I will see you in the next video. Stay tuned and stay blessed. I hope you enjoyed the video. If yes, please do like, share, and subscribe, and share to the people who love mathematics, probability, and all these things, and enjoy them. All the best, and stay tuned and stay blessed. Bye bye.